let's go ahead and get started. So I apologize for having to cancel last week's lecture. I never like to do that, but I was too sick to even stream. So we'll finish up chapter 8. I did have a quick announcement, if I can find the flyer. So maybe you've seen it if you've been around the building, or maybe you've gotten emails. So there's a summer barbecue tomorrow. So Wednesday, June 8th at the Medford campus, so 12 to 2. I've been told that there was a dunk tank, and I did sign myself up for that, so you can get out your aggression if you have any aggression. At least I assume that's the plan. Like I said, I'm not in charge, just volunteered. And then just a couple of reminders. So this is our last week of class, so last week of lab. So last lab should be fun. It's a titration, so that should be a nice last lab. And next week, we'll do a review on Tuesday, and exam will be open on Thursday. And those of you who want to take it in person, we'll take it starting at 4 p.m. on Thursday, so during our official recitation time. Any questions about anything before we get started here? Watching the chat, welcome chat. All right, so let's go ahead and finish up our freezing point depression. And so freezing point depression, you saw this in lab. So you probably saw you made your rock salt bath and the temperature of that lowered. And so that's also why, they salt the roads and stuff. Of course, now it's nice and warm, so we're not seeing the salt on the road currently, but think back just a couple of months, they salted the road so they could lower the freezing point of water and so turn any ice back into slush on the streets. And so all this is saying is the freezing point of a solution is lower than the freezing point of the pure solvent. So that's why we have freezing point depression, so it's lower. And so there's just a formula for this. So the difference of this temperature, so what we expect the normal freezing point to be, and then versus the freezing point of the solution, the difference of that is equal to, and this is given in molality, so remember little m, molality, times this Kf factor, which this would be another one of those constants that you would have to be given or look up. So this Kf is just dependent on whatever the substance is, so you have to look up the value for your substance. And then that is given in degrees Celsius per molality. So you could see, molality times degrees Celsius over molality. So that gives you degrees Celsius for your delta T. And I like this chart here. So if we look, so here's our melting point curve on this line. Let's highlight this. So this is all melting. So we have our solid to liquid line here. And so notice for our pure solvent, it's higher versus the solution is lower. So again, that's our freezing point depression. And so thinking back to water, so we know that pure water freezes at 0. And at this temperature, ice and liquid are at equilibrium. And so salt disrupts this, so now it disrupts the packing too. And so now the salt dissolves in water, and it's not easily attached to the solid ice, so now you get the melting. And so when an aqueous solution containing a dissolved solid solute freezes slowly, that ice then that forms does not normally contain much of the solute. So just saying, if you do have a bit of ice, then you probably don't have whatever your dissolved substance in there. And so now to return to equilibrium, now the temperature has to be lowered sufficiently enough so that the water molecules slow themselves down and then reattach back to the ice. So now this is just a KF depending on your solvent that you're looking at. So for example, if you were looking at a solution in benzene, you have its normal freezing point, then that KF factor. And of course we'll look at KB in a second for the boiling point. And so water has a normal freezing point of 0, and its KF factor is 1.86. So again, you'd have to look at a chart, or I would give this to you on an exam. So let's try this one. So what is the freezing point of a 1.7 molality aqueous ethylene glycol solution? And the key word here is aqueous. So I'll give everyone a minute or so to work on that, and then we'll go over the answer. Looking for answers. Do you have an answer yet? Let's look at this one together. So let's go back to our formula. So our formula is just delta T is equal to molality times our KF. And again, a lot of this is just dependent upon that KF value that it was given to us in the Celsius per molality. So again, you may see different units. And then the other kind of thing that I was trying to point out in this hint to you is that we don't really care that it's ethylene glycol, but we do care that it's aqueous. So we have this ethylene glycol dissolved in water. So we want to look at water as kind of our basis point and also the KF to use. So now we can plug in our formula. So delta T is equal to molality times KF. So we were given our concentration in molality. So I'll go ahead and plug that in. So 1.7, and then its KF factor for water is this 1.86. So times 1.86. And so we can plug that in to get the delta T. So now we should have this delta T of 3.16, or I'll round to 2 since we only have 2 6 big, so 3.2 degrees Celsius. But this is just our delta T. It's asking for what's the freezing point. So we can look at our chart. So the normal freezing point for water is 0. So then we know our freezing point is just 0 minus this 3.2. So negative 3.2 degrees Celsius is our answer there. Any questions about that? Did you get that? Sweet. So we had freezing point depression and now boiling point elevation. So there's our key word. And so the boiling point of a solution is higher than the boiling point of a pure solvent. So once again, we have the same effect. And maybe you've heard of the great salt pasta debate. So people will debate, should you put the salt in the water when making the pasta? So technically, if you put some salt in, right, it would have to boil then at a higher temperature. So maybe your pasta would cook faster, but depends, you know, if you start timing when the water's boiling, or if you put the pasta then the salt in. Anyways, it probably doesn't really matter. But it's just a great debate that people like to discuss. But what we care about is now this analogous formula. And so we have our delta temperature of boiling point is once again equal to our molality times our Kb. And so let's look at this chart again to check out the boiling point elevation. And so now we're looking at our liquid gas curve here. And so if we look pressure, temperature, so temperature is on this axis here. And so if we look at our liquid solution, so now this is our original, and now our solution is higher. So now we have to go to a higher temperature in comparison to get that boiling going. So again, boiling point elevation, so it takes more energy to break up all those intermolecular forces now that you have more molecules in there disrupting everything. And so now let's try this practice problem. And so instead you'll have to reference this Kb factor. And so water, the Kb factor is 0.512. And so now we have what mass of ethylene glycol in grams must you add to 1 kilogram of water to produce a solution that boils at 105 degrees Celsius. And it tries to give you a hint that pure water boils at 100, so your delta T is 5 degrees. So take a couple of minutes. How would you solve this? And we'll go over it. So we have this one, delta T is equal to M times Kb. And then if you need the Kb factor, it's 0.512 for water. Try to leave it there. Molality. So yeah, it's that little m. So we'll write it out. Molality. And so remember that was moles per kilogram of solution. Let's start going over it together, and y'all can tell me what you got. So we'll start with our setup. So we have delta T is equal to our KB times our molality. So if we read over the problem again, right, we have our delta T. So our delta T is 5 degrees Celsius. We have our KB, so that's just a constant. But then we're trying to find, well, in this case, we need molality, right? And then, sorry. And so, of course, we could set up molality is moles over kilogram. And then our problem tells us, okay, well, we have 1 kilogram of water. So we could substitute this in, so 0.512. So that's going to be moles over 1 kilogram. And so now this is our x that we can solve for, or at least for moles. Eventually we'll have to get to mass. And so first I'll just start with that. So 5 divided by 0.512. And then so this gives us 9.76. Is equal to moles per kilogram. So this is what we got for moles. 9 moles. So now that we have 9.6 moles, we just have to find the mass of ethylene glycol and multiply it. So what's our molecular weight of ethylene glycol? So 62.068. 0268. So if we multiply this by that, and so do we get a final answer of 605 grams to make our solution change?
To multiply the
Yeah, so I did 62 times that 9.76 to get that final, since it was asking for mass. Oops. Go away. Yeah, and 62 would have been fine for the mass, as long as you got somewhere for your final answer around 606 grams or so. Excellent. So the last little section here. So osmosis is just defined as the flow of solvent from a solution of low concentration into a solution of high concentration. And so usually you have some sort of semi-permeable membrane that allows this to occur. And so it allows solvent, but not the ions to flow through it. So in this case, we have our semi-permeable membrane, and then on the right side over here, we have a solution of mainly just water, pure water over here. Then on the left side, you have water with a bunch of solute particles. And so the water is going to flow from the right to the left to try to equilibrate this. Since again, we have low concentration to high concentration, so it's going to flow and try to dilute this. And then if you were to try to exert a pressure to stop this backflow, that would be known as the osmotic pressure. So that's just defined as that pressure. They show us, of course, a difference here since they did allow it to occur, but it's defined as the pressure to stop the flow. So that's your osmotic pressure. So again, define the amount of pressure needed to keep osmotic flow from taking place. And so the part that we care about is that it's directly proportional to the molarity, but then we also have to take into account how many particles we form. So there's a little caveat to this. And so really, I don't quite like how they've written this formula. I would rewrite it as osmotic pressure is equal to I mRT, which will look at this I is this Van Hoff factor, which we're going to take a look at right now. And so this Van Hoff factor, it's just basically saying, well, how many particles in solution do you make? And what we mean by that is, let's say you have a non-electrolyte, like sugar. So we know sugar is just one big discrete molecule. So you put 1 mole of sugar into solution, you still have 1 mole of sugar. So that didn't change. But now let's look at, so sodium chloride. So let's say we have, right, a 1 molar solution of sodium chloride. We put it into solution, but then we would get 1 mole of sodium ions plus 1 mole of chloride ions. So now we have 2 moles total in solution. So does that make sense? So now that one discrete ionic compound separated, of course, into 2 in solution. And so that's just this factor here. So the measured in reality, I guess molecules don't actually disassociate fully, so hence why you have all these kind of funny decimal factors, but for our purposes, we just want to go with a simple expected one. And so that would mean for, let's just do magnesium sulfate, we'll go down these examples. So magnesium sulfate, so we know that's just an ionic compound, and we know that sulfate is going to stay in solution as one big polyatomic. And so again, we start with 1 molar. So now we have 1 molar of magnesium, 1 molar of sulfate, giving us a 2 molar solution total. So if we were to do this with magnesium chloride now, so of course start with 1 molar of solution, we would make 1 mole of magnesium ions, and then now we have a 2 factor here, so now we make 2 molar solution of chloride ions, giving us 3 molar solution total. And so continuing on, so what about iron trichloride? So if you had 1 molar of iron trichloride, how many moles total would you have in solution? So 4, exactly. So 1 mole of our iron 3 in this case, plus the 3 equivalents of our chloride. So that gives you 4 molar solution total. And so if you're comparing solutions, so just like we were doing, we're comparing 1 molar solutions, but to compare the osmotic pressure, you need to use the kind of Van Hoff factor one and take into account how many ions would form. And so this also applies for like freezing point depression, boiling point elevation. So if you're just kind of comparing, so again, like a 1 molar solution of sodium chloride versus a 1 molar solution of magnesium chloride, the 1 molar solution of magnesium chloride would have a greater effect since it's effectively 3 molar in solution. And so I think that came up on the homework. So I don't want to go into the point anymore, but we need to revisit this, we can. And so quickly, to round out this chapter, some terminologies. So isoosmotic or isotonic. This just means that the solution on the outside has the same pressure as the solution on the inside. So they have the same concentration, right? So there's no net flow of water in or out of the cell, so they'd be going at the same rate. But now, let's see how you would get a shriveled blood cell. So this would be if you had a hyperosmotic solution or a hypertonic. So hyper, of course, meaning more than. So this means that your solution has a higher osmotic pressure, aka more particles. So if it has more particles, then that's going to cause water to flow out of the cell. And so you can kind of think about, right, you eat a bunch of salty snacks, and this is what could happen to your red blood cells. So now that your blood is full of ions, you could kind of shrivel a little. And so now the opposite would be hypotonic or hypoosmotic. So again, hypo meaning lower. And so if the solution has a lower osmotic pressure, aka, right, less ions in solution, that means that the water is going to flow into the cell. And so this is why, like, the gallon challenge could be potentially dangerous. So you drink a whole bunch of water, right? So now you don't have ions in solution, and so that's going to drive water into your cells. And of course, if it gets bad enough, right, these blood cells can burst. Yep. All right, I think that's good for chapter 8, unless there's any burning questions or anything that we should go over.
How much water does it take to kill a man?
I don't actually know. All right, so let's look at acids and bases, our last chapter. And so let's start with just general properties of acids and bases. So for acids, and you're probably familiar with some like lemons or orange juice. So if you taste an acid, it would have a sour taste. We've learned throughout our lab journey that many of these acids can dissolve metals. So you've seen that with hydrochloric and nitric acid. And then of course, they neutralize bases. So we have, citric acid in lab to neutralize any base spills. So there's our hydrochloric and acetic acid. So acetic acid, if you remember, this is a weak acid, and that just has to do with its dissociation, not with how harmful an acid is to you or anything. And so they would change blue litmus paper to red. And so some common acids, so hydrochloric, that's a major component of stomach acid, and it can also be used for metal cleaning or maybe food preparation. Sulfuric acid is used a lot in batteries or electroplating, or definitely fertilizer and explosives. Nitric acid is also a big component of fertilizers and, once again, the explosives. Acetic acids, you already know that's vinegar, so obviously that's also going to be part of food preservation. Citric acid, so that's found naturally in lemons and limes. And then, of course, you've seen that big thing of citric acid we have in labs, so nice solid powder. And so this is also used to make candy, citric acid. Carbonic acid is just basically in solution from CO2 reacting with water. So that's just in equilibrium, and so it's going to be present in carbonated beverages as well. And then there's HF. And so HF is used for metal cleaning or glass etching, frosting, and I think also making like silicon chips. And then phosphoric acid would also be used in fertilizers, and then it's used a lot in biological buffers and in your soda. And so these organic acids are structured a little differently. So they have this carboxylic acid group, which we'll draw out like so. So this is a carboxylic acid. That's what it means when they write this COOH. There's our carboxylic acid. And so acetic acid, citric acid, all those have a similar form. And so only this proton is acidic. And so why it's acidic is it's essentially really favorable to deprotonate. So let's look at this a little more detail. So we have our carboxylic acid. And so water can come along and act as our base here. So these electrons from oxygen pluck off this hydrogen. So these electrons go back then to the oxygen. And so that gives us this resonance structure here. Now it has a negative charge, but then we can move these electrons around, and this is why these carboxylic acids are stable, why that's considered an acidic proton. So what we can do is we can form a double bond here, but we can't have 5 bonds to carbon, so that means that these electrons are going to be kicked up to this oxygen, and so now I'll rewrite it like so. So we just kind of move the charge from one oxygen to the other. Sometimes you also see this rewritten like this, kind of these two partial double bonds, and then they put this negative charge here. And what they're really trying to show, and why this is stable, is this whole negative charge is delocalized across this whole area. So it's delocalized right across these two oxygens, so that makes it really favorable since it's really resonance stabilized. So now looking at bases, and I don't know if anyone's ever had their mouth washed out with soap, but hopefully you haven't. If you have, or you accidentally ate some soap, you know that it tastes kind of bitter. So bases tend to be bitter tasting, so they're often poisonous too. I can't really think of too many bases that you eat, but they also kind of,
You don't eat soap?
not regularly,
But
no.
it smells so good.
Did you taste it though?
It's a little bitter, but
There you go, see, a little bitter. And so all these bases,
coffee.
they feel, slippery to the touch, so you probably know that about soap. And then if you've touched, bleach or ammonia, you know that those also kind of have that slippery feeling. They can neutralize acids, obviously, so we have our bicarbonate in lab to neutralize acid spills. And of course, they would change the red litmus paper blue. And so these are just kind of the common bases. So sodium hydroxide, so that's used a lot in soap manufacturing. If it's not sodium, then it's potassium hydroxide to make soap. And it's also used in batteries, all sorts of processing. So sodium bicarbonate, that's our baking soda. And also an antacid, you can
It's a
have,
water softener.
yeah, water softener for sodium carbonate. Can also be used as just a cleaner. And then ammonia.
Not now.
So ammonia is obviously fertilizer, and then also explosives, and apparently detergent. All right, so now let's talk about this hydronium ion. And so all this is saying, and water is pretty cool, like this. So water has basically the ability to undergo autoionization, meaning it can ionize itself. And so really what this means is you have two water molecules, and one of them can come along, pluck off the hydrogen from the other one, and so that would give us a small amount of hydroxide in solution, and then also some hydronium. If I can draw this out. And so what this is trying to emphasize too, and I do this all the time, is so chemists are lazy. They're not going to bother to write out H3O plus a million times, and you have a lot of mechanisms that depend on proton transfer, kind of going back and forth. So you always see chemists writing this H plus colloquially, but this is just emphasizing that you don't actually have just naked H plus floating around. So anytime you see H plus being written or drawn, know that they really mean hydronium. Unless you're like actually talking about some really weird proton transfer mechanism that was quantum based, but that's like the only exception. So when we're talking about this like acid base chemistry, it's hydronium.
Okay, that makes more sense.
And so like we were looking at here, so it can react with itself to form hydronium and hydroxide. And so there's where it says chemists often use the simplified hydronium interchangeably with H+. So you'll often just see H+.
So H plus H2O equals H plus?
Yeah, I think this is just a bad schematic, but I kept it there. And so now let's look at these different definitions of acids and bases. So we'll start with the Arrhenius definition, and then kind of work our way. So let's look at the Arrhenius theory. So again, it's the simplest, and all this is saying is an acid is anything that produces H plus ions in solution, so such as our HCl, or any other of kind of our common acids. So we could do nitric acid dissociates. Or sulfuric acid. So we could go on and on. So that's, again, our acid, anything that produces H plus ions. And so bases would then be anything that produces hydroxide ions in solution. And so again, this is just a simplified overview. So this would include potassium hydroxide, magnesium hydroxide, and so with these Arrhenius acid-base reactions, so of course we know that the H plus from the acid adds with the OH ions from the base to make one molecule of water. And so they just say, think of water as HOH, and so that just helps you remember that this is your hydronium, and this is your hydroxide part. And so in these neutralization reactions, which is also, we were touching about like 2 weeks ago now. And so in these neutralization reactions, we have our acid plus a base forms our salt plus water. So if you think back to when I was trying to like poorly describe those double displacement reactions, the last case that we didn't cover explicitly was this acid-base neutralization reaction. And so if you notice, so of course salt, that's still soluble, but the formation of water drives the reaction. So instead of precipitating something out, we have water formation, and so that again is going to drive our reaction all the way to equilibrium. And I'll just add in here, right, so this is a double displacement, or a type of a double displacement. So you could call this double displacement slash neutralization reaction. And so, you know, ultimately you're just swapping partners around. So there's your sodium chloride, and of course there's your HOH for water. And so the problem with the Arrhenius theory is that it's too narrow. And so it doesn't really tell us why ammonium makes a basic solution, right? So we can't just split ammonia into hydroxide. So it doesn't really show us what's going on here. And it also does not explain how some ionic compounds, such as sodium carbonate or sodium oxide, dissolve in water to form basic solutions, even though they don't contain hydroxide ions, so that's not accounted for. It doesn't explain why CO2 dissolved in water forms acidic solutions, and so this does not explain acid-base reactions outside of aqueous solution. So now we go to our kind of next definition, the Bronsted-Lowry acid-base theory. And so now this is kind of based on what happens in a chemical reaction. And so any reaction that transfers a proton from one molecule to another is classified as an acid-base reaction. And so that means that an acid is a proton donor. That makes sense. So you can still think of HCl kind of donating that proton. And meanwhile, a base is going to be a proton acceptor. And so usually that base is trying to, really I want to say that the lone pairs are attacking that H+. And so this is kind of the Bronsted-Lowry definition here. So we have HA for acid, and then our base. And so now our base can just be something that accepts this acid. And so if we look at this under our Bronsted-Lowry definition for HCl, HCl is the acid since it transfers its H plus ion to water to form hydronium. And so water in this case would be acting as the base. And so we have our acid here. So once our acid loses the proton, it becomes the conjugate base. So now it's a base. And then we have our base here. So after our base reacts and picks up a proton, it becomes the conjugate acid. And so now this finally explains why ammonia is the way it is. And so for ammonia, and this goes back to its Lewis dot structures as well. So we have ammonia in solution. It has that lone pair and some water's hanging out. And so this lone pair on the nitrogen can go ahead and pluck off this hydrogen from water. And so now that gives us our ammonium. So now this would be our conjugate acid, or rather this can act as our acid now. And that makes our hydroxide. So now it's a product of our acid-base reaction. Now it's a base, so this is our conjugate base here. And so it kind of helps illustrate this equilibrium as well. And so for weak acids, this would totally be reversible. So that proton from acetic acid, let's say, so it gets deprotonated, makes our conjugate base of acetate. Then that acetate ion can reform. So that's what's going on now down here. Let's write this out. So acetic acid, HC2. What's acetate again? I'm totally blanking. So C2H3O2. So there's our acetic acid. Water's acting as our base here. Then we form acetate. Then our conjugate acid would be water. And so in this weak acid case, we have this equilibrium where it can reform. So that means we're going to have our acetate, and I can draw it like this as well. So we have acetate plus, so now we have our water, right, our conjugate acid water. And so since, again, it's weak, that means that this is a strong enough base that it can go ahead and take back this hydrogen and then reform our acetic acid. And then giving us back our water as a base. And so you should have noticed that in this Bronsted-Lowry acid-base reaction, so the original base becomes our conjugate acid, and then our original acid becomes the conjugate base, and you can see that relationship. And so you have your conjugate pair, and so your conjugate pair should only differ by a hydrogen, and so your base should probably have less hydrogens than your acid. So right, ammonium here is your base, add an acid, add a proton. Now we have our conjugate acid species. So this would be our acid, and then it can react with water. So water would pick up that proton and reform base. So looking at this water hydroxide acid-base pair, so in this case, this is acting as the acid, remove a proton since it's acting as the acid, and then you get its conjugate base of hydroxide. So before we do that, so I want to emphasize, so hydroxide and hydronium, this would be not an acid-base pair. So that's how I might try to trick you. So I didn't put water, right? You would have to have water in between these. So we could say that hydroxide and water, so that's an acid-base pair. And water and hydronium is an acid-base pair. But again, you can't have those two. So
Why not? Sorry.
because there's more than one hydrogen difference between them.
Okay.
Because with these acid-base pairs, you're just adding or removing a hydrogen. And so these would just not be considered pairs. They don't have that relationship, since you would have to add too many protons. And there's like a step in between.
So would they still react? They still react together, though, right?
Yeah,
They're just
so
not acid-base.
they would
Okay,
be-
yeah.
Yeah, they would react, but they're just not considered a conjugate acid-base pair.
Okay, that makes sense.
Yeah, so conjugate acid-base is just like that definition.
Never mind, that makes sense.
All right, so take a look at these two reactions. So the first one, we have sulfuric acid reacting with water to give us H2SO4 minus, or sorry, HSO4 minus and water, or hydronium. And then the bottom one, we have our bicarbonate reacting with water to give us carbonic acid and hydroxide. So take a minute or two, who's the acid, who's the base, and who would be the conjugate acid and conjugate base then? So let's look at A together. So this H2SO4, is this the acid or the base? So it's our acid, so good. And we can tell that since it's losing a proton. And so if this is a base, what does that, or if this is the acid, what does that make water?
The base.
So base, good job. And so this HSO4 minus, is this our conjugate acid or conjugate base?
conjugate base because it has, or isn't it not because there's more than one difference? Like not a conjugate because there's
Well, it has to be a conjugate something,
not a
but
conjugate.
yeah, yeah. Yeah, so it should be the conjugate base. And so you can just remember, if it was the acid, then it should be the base now. And yeah, you can tell though it did lose that hydrogen. So comparatively, it has less than our original acid. So now it's our conjugate acid-base pair. So just that one hydrogen difference. And then, so what does that make water now, or this hydronium species? So now it's our conjugate acid, so it could act as an acid now. And of course, this one, HSO4 minus, is tricky, and it could confuse people since it can go on and deprotonate again to just make sulfate, but then that would mean, right, that these two are a conjugate acid-base pair, but not sulfuric acid and sulfate, right? So we have that same thing again where these are an acid-base pair, and so that means sulfuric and HSO4 minus are a conjugate base pair, but not the further ones. And then so B is bicarbonate, our acid or our base. So our base, exactly. And so that was an excellent observation. So you could tell that it picked up a proton, so comparing. And so this is our base. What's water? We already have a base. So water can be an acid or a base. Acid. And so now our carbonic acid, so is this our conjugate base or acid? So excellent, so conjugate acid. And so that makes our hydroxide our conjugate base. Any questions about that? Oh, all right. One last thing before we move on. So we didn't go over the last definition. So we had done Arrhenius, Bronsted, and so let's just look at Lewis acceptors and kind of why they're there and what substances would fall under it, and then we'll kind of move on. And so Lewis definition is the most expansive, and so this is based on electron donors and acceptors. And so acids are any substances that need or accept an electron, and bases donate an electron pair. And so a really good definition and example of this is this borane adduct. So we can have BF3, and then ammonia can come along. And so why I drew it like so is I'm trying to emphasize here that those two lone pairs from ammonia, that they are both being donated to the boron. And so now this is an excellent Lewis acid-base pair. So we have our ammonia. So we already kind of know it's probably going to act as a base from our Arrhenius definition. But now if we look at our Lewis definition, okay, so bases are anything that donates an electron pair. So we have our ammonia donating its 2 electrons, and that means that BF3 here is going to be an acid since that borane is able to accept those electrons. All right, so now let's move on. And so now let's go back and talk about this strong acid base versus a weak acid and base. So we've kind of touched on this a little in terms of electrolytes. So we mentioned that a strong acid is a strong electrolyte, which means it has complete ionization of our acid molecule in water, or anything that, again, completely disassociates. All we're saying is that it breaks up completely, like so. And so for a weak acid, only a small percentage is ionized, so that means we have this equilibrium. And I'm going to put HF as our example. So HF is a weak acid, and again, it's only considered a weak acid because of this equilibrium, right? Because HF is pretty nasty. I think I've talked about how nasty it is. So it has, again, nothing to do with its strength or how nasty it is, just its behavior in solution. And so same thing, a strong base is a strong electrolyte, so it's going to have complete disassociation versus something like ammonia, where only a percentage is ionized. So now we have, again, equilibrium of this ammonia versus ammonium species. And so let's look at some general trends. So the stronger an acid is at donating a proton, the weaker the conjugate base is at accepting a proton. And let's break this down a little bit, because we say it all the time, but we really want to understand what that means. And so what that is saying is if we have this strong acid, like HCl, so the stronger the acid is, that means that the weaker the base is. And so this is essentially so weak of a base that it cannot pick up a hydrogen. So chlorine is essentially such a bad base that it's not going to reform with this H, so it can't, what it's not going to do, it's not going to pluck off anything, right? Because it could theoretically do that, but that doesn't actually happen in solution, so it cannot reform. And again, that's why you have this arrow there saying your equilibrium lies all the way to the right, and it's all going to be disassociated. And so these are just kind of general trends. So higher the oxidation number, the stronger the oxy acid. So more oxygens, more oxidizing potential. That gives you the stronger oxy acid. And so sulfuric is, of course, a lot stronger than sulfurous. And so nitrous acid is, or sorry, nitric acid is stronger than nitrous, just because it has another oxygen. And then cations tend to be stronger acids than the neutral molecule, and neutral molecules would be stronger acids than the anion. And so I like this chart a lot because, again, it tells us a lot of different things. And so first thing you notice is it has all your strong acids up here. And it also reminds you, so undergo complete acid ionization in water. So that's telling you, again, it's not going to reform. You're not going to have, bromine forming HBr in solution. So all these conjugate bases, so iodine, bromine, chlorine, right? All those are terrible, terrible bases.
Yeah, acids? Oh, never mind. Sorry. Never mind.
Yeah, no, I get what you're saying. And so it has the base on the other side, so it reminds you, do not undergo base ionization in water. So all this is saying is they're not going to reform. And so these are 4 bases. And so we have increasing acid strength on this left side here. So perchloric is the strongest. And going down, so now we have hydronium. And so, of course, once we hit hydronium, now we can have some equilibrium. So there's our hydrogen sulfate and kind of so forth. So now we have, right, all our weak acids in equilibrium.
What else an acid?
Sorry?
Oh, I just ethanol is an acid.
It would be a very poor acid. So do not undergo acid ionization in water, so not really. And then on our base side, so increasing base strength, so now these are all our conjugate ions, so we have HF and fluoride, and so they're just counter ions. So increasing base strength, and then, so these would not reform, so undergo complete base ionization in water, so you're not going to reform anything with those. So our strong acids, so this is kind of re-emphasizing and hopefully solidifying all these things. So a strong acid, it has 100% ionization, and that means its Ka is going to be much greater than 1. Just remember that Ka was kind of our equilibrium and just generally products over reactants. So if for a strong acid, it lies all the way to the product side, and it's going to be greater than 1. And then we have, so we care about the concentration, and so all this is saying for a strong electrolyte is if we have 1 molar of HCl, then we have 1 mole of H plus ions in solution, and that's all that's meant with these little brackets. And so you can indicate the solution concentration. So that's all that's meant in there, and so we'll see that we want to calculate pH and other things from these concentrations. And then, so these are the 6 strong acids. So again, you don't have to remember them, just look at them at the top of the chart here if you forget. But it is good to at least somewhat be familiar. So HCl, HBr, and HI, relatively easy to remember. And then you have nitric acid, you work with a lot. Sulfuric acid you work with. So the only funny one you may have to remember is a perchloric acid. And so then again with these weak acids, that means that their Ka is going to be less than 1. So again, we're thinking products over reactants, and since it only donates a small fraction, so now we're going to have some sort of less than 1 ratio. And so this also means that the weak acid does not equal the H plus concentration in solution. And so I can have 1 molar solution of acetic acid, but it does not equal our H plus concentration. So there would be a different formula for this. And so we have acetic acid, carbonic acid, formic acid, so all those are examples of common weak acids. And so we measure the strength of the acid by the Ka. So this tells us essentially what fraction is ionized. You also have the opposite kind of Kb. So our Ka factor would be this one on bottom, so Ka, or on top, I can't speak. So our acid, so all this is our conjugate base, so let's break this down. So right, Ha plus water gives us, now this would be A minus plus H2O, so our Ka would be equal to conjugate base concentration times hydronium concentration over our Ha, original acid concentration. So you could find the equilibrium values for that. Or the Kb, is just based off of this. So we have base, water, and protonated base. And so we could have HB concentration times hydroxide over our base concentration. That's our Kb. And so what we care about is kind of comparing these strengths now. And so now we're looking at Ka, which is again what we want to look at for this reaction. So how much hydronium we'd be forming. And so the Ka of this chlorous acid is 1.1 times 10 to the negative 2. And so if we're comparing that with this cyanic acid, which is 4.9 times 10 to the negative 10, so you're comparing a negative 2 versus a negative 10. So of course this negative 10 is much, much smaller. So this is larger and therefore also the stronger acid. So you can tell the relative strengths of the acid based off of this. Blah, blah, blah. So here's just rewritten our Ka expression. And so again, Ka is just equal to our hydronium concentration times our conjugate base concentration over our acid concentration. And so this is kind of a useful chart. So you have your Kas over here. Trying to judge how far I want to go today too. And so let's look at another relationship. I think it'll come up later in lecture. And so we have our Ka. If you notice, we also have this value called a pKa. And so the lower the pKa, the stronger the acid. But the other relationship is that the negative log of our Ka is equal to our pKa. Or we could take our Ka is equal to our pKa to the power of our 10 to the power of our pKa. Let me rewrite that. So 10 to the power of our negative pKa. And so just to show you, and definitely practice on your calculator. This is one of those units where you have to make sure you can plug everything appropriately, make sure you're in the right base and everything. So if I plug in, let's say I want to go pKa to Ka. So I'll go 10 to the power of my pKa, of the negative pKa, so negative 1.96. And so we move that decimal point over. So that's what they report here for the Ka. So 1.1 times 10 to the negative 2. We could also go from Ka to pKa. So if I plug in negative log, I'm just doing the next one now. 4.6 times 10 to the negative 4th. And so that spits out 3.34. So that gives us our pKa. So you can see that relationship there. All right, I think we should stop there before we get into the next bit. So let's at least, in our last kind of 5 minutes, let's touch on what you're going to be doing in lab really quickly. And so basically you have this titration, and you're going to have a similar setup here. And so you have your base is in your little burette, and we'll go over this more in lab. You can kind of use the You use the difference to figure out how many moles of base you have, so you'll have your top reading, and it's kind of backwards, or at least some people think it's backwards. So it starts off with 1 mil at the top, 50 milliliters at the bottom, and then you want to take your initial starting position, and then you'll eventually subtract it with your final one and get your difference in volume. And then down in this flask, you'll have your acid plus your indicator. And so all an indicator is some substance that changes color at a relevant pH. And in our case, we'll be using this phenolphthalein. So phenolphthalein is here. And so it changes pH around the base level. So it's really good for getting that distinct color change as you go from an acid to a base, especially as you'll see when we titrate. So this is just some examples of what the pH would look like. And so the way the pH kind of goes is, if you were measuring the pH, all right, it's initially acidic, so you're adding a bunch of base to the acid, right? So it starts off low for acidic, so you have really low pH, you're adding base, you're adding base, you're adding base, and boom. And that's when you're going to get that color change. So all of a sudden, your solution's going to turn pink, and you want to do your best to get it as light pink as possible. So I actually think that this pink is too dark in your textbook. So you want like a light pink, and that's how you know you're right there at the equivalence point. And so that means that you've added about the same amount of base as you have acid. And then once you do that, you'll do some math and figure out some moles and stuff. So that will be our basic setup for today. All right, so we'll go ahead and end the lecture. So I look forward to seeing those who can attend in lab. And otherwise, I will see y'all on Thursday for our next lecture. Then I'll hang around on stream in case there are any questions. And then also, if you have questions for the final, you can email me questions, and then I'll make sure to cover them on the Tuesday review session. And then they'll be, of course, available to everybody. And I'll stream it usual time. So thank you, chat. Oh yeah, and then grab your homework, and then I printed out some more solubility rules in case people needed them. So get a copy, and then I can print out more too in lab if we still need more. All right, thanks again, chat. Looks like there's no other questions, so I'm going to end the stream. Thank y'all.